with design. So it goes hand in hand with what we do in design. Okay, so let's have a look here. Don't get confused. You haven't started reinforced concrete. This is just what I do as an introduction to reinforced concrete 3, which I took earlier this semester. So essentially, I just wanted to put the link between the two. When we look at a structural building, and I'm taking a very small one here, with some slabs and beams and columns, just a sketch, right? Analyze this. What are we supposed to do? Okay, because when you get to work, in the old program, you had the in-service training, which was different. The approach was different. We gave you a lot of the theory, and then at the workstation, they did a lot of training. Here, you're supposed things. So you're going to get to your place of work and you're going to find that there's a plan in front of you, probably from an architect, and maybe the first that thing and extrapolate it for use for structures in CAD or BIM or whatever else they're using, right? So that's the first thing you're going to be faced with. In a good company, in a company that is well structured and they know what they're doing and they're training people, that's the first step. And they will see that you're okay with the drawings and understanding of the drawings. Then they'll pull you into design slowly and check your work, etc. If you go into a company where they're busy, they don't know what they're doing, they probably just throw a plan at you and says, right, you do the drawing, detailing, design, everything, and you have so much of time to do it. Okay, with very little guidance, and you'll be in the deep end. So my aim is always to try and help students understand what they're going to face at work. Okay, so I look at it from that angle, right? So what do we do? And we don't have to think too much about this because the code has actually told us what we can and cannot do. So we break this 3-dimensional structure, okay, into 2 dimensions. We don't have to. If you're doing it on the computer, you can do it as 3D, but because we're talking about hand analysis here in our course, we will be doing computer analysis as well, but more as an introduction. Here we want to get to grips with how to do it by hand so we understand what's going on. All right, so we break it up into 2 dimensions, right? So now we have a skeletal structure in 2 dimensions in each direction. And of course, we're able to extract the loads from the slab onto the beam, from the beam onto the column, from the columns down to the foundation, etc. And then the code talks about how we can do the analysis of this frame that we've broken into a 2-dimensional frame. So here's an example. It says we can take one level, okay, and the associated columns above and below. We can do the whole thing as a frame like that on the left in figure 3, or we can break each floor up into something like this. And then we can even go smaller, okay? So if we've done a beam analysis using moment distribution, we could even break it up into something smaller than that. Sorry, I mixed it up a little bit here. This one is a subframe, which is smaller than the previous one. So you're looking at that beam, the design of. Give my second. So what I'm saying to you is, okay, in this subframe analysis, your object is to try and get the results for that one, and you will obviously look at that column, those 2 columns. So that's what your focus is on. And so you are moving from this analysis there, that approach. So this is full. This is the full one. In, of course, 2 dimension. This is a level. So taking one level at a time, right? And this is taking one element at a time, right? You look at the continuous beam simplification. So you look at the beams in isolation and you treat them as continuous, and you have to all spans loaded. There's options about this, all right, and slightly different for our new South African code is going to be the Eurocode option of dead and alive loads factored on adjacent spans. All right, a lot of this will be Greek for you because you haven't come across design at all yet. And then this is what you do in the analysis. Okay, I'm just giving you a peek into what happens in the introduction in reinforced concrete design 3. Right, so there we have the analysis for one of those beams. There's a long way of, and then there's a short way of, and a shorter way of doing it. All right, so there's a couple of approaches of how you can do this. That's the shortest route. At the end of the day, this is what you come up with. Bending moment envelopes and shear force envelopes, and you design for this, okay? And then I go on to discuss how you design the columns, what you do for the columns, now that you've chosen this particular approach. So it goes into all of this kind of thing. But what I'm trying to show you is right here is we're starting with this, okay? And in our case, we're not looking at 3D analysis, we're looking at 2-dimensional analysis at this level. So we want to model our structures in 2D, load them and analyze them, but it's fitting into where? It's fitting into the design, whether it's steel or concrete or timber or whatever else. It feeds into that process. Okay, so just as an introduction, that's where we're going in terms of what are we talking about in analysis. It's not something it's sitting in isolation. It's part of your whole design approach. Okay, any questions, guys, for the introductory part? Any questions? Just whenever you have a question, just pop in and ask it, all right? Just go ahead and interrupt and say, I don't understand this, so could you repeat that? Or, okay, when we're in the classroom, it's going to be a little bit easier, but for now, just stop me when you don't understand something. Okay, so the first thing that I want to clear up is degrees of freedom. Now, you did in mechanics, if something is given to you, able to say whether this is determinate or indeterminate. Okay, so you had, for example, you had you'd have probably been asked, well, if you got a beam like this, is it determinate or indeterminate? If you had a frame like this, can you categorize it as determinate or indeterminate? So that's the kind of stuff if you covered in mechanics, and you realize then that, hang on, I can't solve these two problems. What the reason? Why couldn't you solve this problem? So A and B, right? Why couldn't you solve A or B using mechanics? What was the problem? Okay, let's look at the determinate or indeterminate. Is it statically determinate? Any one of them statically determinate? Statically determinate means, in simple lay language, we say that, can you use sigma H, sigma V equal to 0 and sigma M equal to 0? Can you use these three equations to solve the problem? So let's go to this first one. There's a beam which has supports, pin supports at A, B, and C. It has a particular load from A to B and maybe a different load at B to C. Okay, so can you solve that? And for a given loading,
Yes.
and a given span. Okay, can you? Okay, guys, can you still hear me? Hello?
Yes, sir.
Yes, sir. Okay, this network seems to be a little bit No, it's going up and down. All right, okay. So can you do that analysis? Any one of you can respond. Can you solve for the continuous beam A, B, C? If I gave you, okay, well, why not?
Too many unknowns, huh?
Why not? What do you see as the unknowns?
VA,
What are the unknowns
VB,
in?
VC.
Okay, so when you, so basically first starting off, there's only vertical loads, right? So we know that it's sigma H. All right, I won't take it out. Let's say that we know that sigma H is not really going to help us because the horizontal reaction at A, the horizontal reaction at B, the horizontal reaction at C are all zero. In sense, okay, all those reactions don't exist because the load is purely vertical. Those will fall away in any case. There won't be any. All right. So we've got the unknown reaction at A. We've got the unknown reaction at B. We've got the unknown reaction at C. So at a very fundamental level, we don't know the reactions. If I gave you, let's call this figure C. If I gave you figure C, can you solve the problem? Sorry, we didn't complete A, but let's go to C first. If I gave you A to B is a simply supported beam. You have a pin on the left and a roller on the right-hand side. You have a triangular load. It could be any load, okay, just to keep it simple. Let's take the triangle out and just keep a UDL on there, right? Let's just put a UDL on it for now. Okay. Can you solve this one?
Yes.
Yeah. Okay, how are you going to solve it? Just the approach.
I can take moments about either A or B.
Correct. All right, 100%. So you start off by taking moments at A or B, as you said, because there's only vertical loads here, right? Another story, if I put in a load like that, okay, then I've got an inclined load, then I've got a horizontal component, and I've got a vertical component. Okay, and I've got a vertical component. Horizontal is only one place that I can take it, so I can resist it. B is a roller, it won't do anything. So it's resisted at A. So whatever the horizontal is on the beam has to be resisted at A. That's no problem. Taking moments about A. For example, I will have the vertical reaction at B, okay, which will come out of that calculation. If I take moments about B, I will get the vertical reaction at A. So once I've got those two reactions, I can then go on and draw the shear force diagram, whatever it may be due to that point load. It may come like that. And then I can do the bending moment diagram. Okay, so I'm able to solve that without any difficulty then. Are you with me? Right, but in this case, I'm starting off with a problem in A, is that I have three unknowns, okay? Well, it doesn't sound like a real problem because I've got three equations, but when you look at it, I have nothing horizontally and it's not giving me anything. So if I take sigma H is equal to 0, there's no horizontal external load, okay? Then I have the horizontal reaction at A, the horizontal reaction at B, the horizontal reaction at C. Okay, common sense is telling me that they don't exist. So, okay, I'll just disregard that. Then I take vertical equilibrium. So I've got take moments about A, I've as an unknown, VC as an unknown, okay? And then of course the loads will create. And then if I take sigma M, sorry, my apologies. If I take sigma V, I've got the loads and then I've got two unknown reactions. If I take the moment, I'm taking my the loads going down, right? And then we have the reactions which are going up. So we're taking the difference between the loads and the reactions. Unfortunately, this doesn't give us an answer. I've got three unknowns and I know the loads. So I'm sitting with three unknown values summing up to a load. If I take the moments, then I've taken moments about A, I have B and C as unknowns. If I take moments about B, I've got A and C as unknowns. If I take moments at C, I've got A and B as unknowns. So I could generate all these equations and I take it, and really where would I go with it? I don't really know. Okay, so same thing here. If I take this structure, it's got some load on it. Okay, let's just put a bit of a load on this thing. So let's say we have a UDL and a point load. Right, we know that we're going to have some reactions, but again, we got a problem because how I'm going to solve all these reactions, I don't know. Okay, right, my three basic equations are not enough, are inadequate to help me solve this problem. So at this level, we're concerned with indeterminate structures, right? Any questions? So basically, this is just serving as an introduction. All we're doing is we're looking at indeterminate structures. That's what I'm trying to highlight. And why are we doing this? Because we're not going to be able to do any design work unless we understand two things, which is loading, which will be covered in Introduction to Design, and the analysis, which I'm covering here. Okay, the approach and how we do it. Right, so first thing I want to start with, I said we spoke about whether structure is determinate or indeterminate. Okay, we had the one span beam with the pin and a roller, statically determinate. Reason, reactions are 3, 2, 1 vertical, 1 horizontal on the left, and 1 vertical on the right hand side. So 3 unknown reactions. I have 3 equations, solve, no problem. Okay, the second one, unknowns are more. Okay, I have 3 unknowns, 3 times 2, which is actually 6 unknowns in terms of reactions. 3 of them I can disregard, but then that takes out the sigma h from the equations, and I'm left with 2 equations and 3 unknowns, which I can't solve. Okay, so as previously discussed, okay, in analyzing a structure, we break it down into a series of discrete members. So I showed it to you when we started discussing what I do in reinforced concrete. Okay, so we break it down into discrete members, and then so this structure basically, let's take the simplest one, which is perhaps a 2-span beam. Okay, so what we're saying is we're breaking it down into member 1, member 2, node 1, node 2, and node 3, right? So we're identifying how we're going to input the structure, what we're going to look at when we talk about it. Okay, degrees of freedom. So we're interested initially how the joints move. So let's start with this first. So basically degrees of freedom in general for structures ways in which the joint can displace. So if we take, let's take a portal structure like that. Okay, I have joint A or node A, node B, node C, and node D. All right, if I look at joint B, for example, if I load this thing, if I keep my focus and my attention on that, if I load it with, let's say, a force here, all right, then I can see that this is going to deflect like that almost, all right, and thing like that. Okay, so we'll get more into this in qualitative analysis, but for now, so I know it's going to do that. So when I look at this thing here now, that joint has moved to that particular point. So there's a vertical, horizontal deflection. There may be a little bit of a vertical deflection, and there's a rotation that has taken place. Are you with me? Does everybody understand? And when we come into the classroom, I will show it to you with a model, okay? With a little model so you can understand it even better. In general, so this is what can happen is at any node, 3 possible displacements, all right? Possible, not always, but 3 possible displacements. 2 of these are linear. That means these are linear rotation. So this is the one that is rotational. Okay, all right. The 2 linear displacements can be in any chosen directions, but we normally make it at 90 degrees to one another, right? So that we can get it working in a sensible direction. Okay, if a joint is free to move in all 3 of these directions, that's 2 lateral and 1 rotational, it is said to have 3 degrees of freedom. Okay, so if a joint is free to move in all 3 of these directions, 2 lateral and 1 rotational, it is said to have 3 degrees of freedom. Don't confuse this with degrees of determinacy. This is something else. You're just looking at it moving, right? If it is free to move in 2 or even one or even none of these directions, then it is said to have 2, 1, or 0 degrees of freedom, respectively. A joint is prevented from having a particular degree of freedom by the insertion of a particular support. The following are some familiar support types and the associated number of degrees. Fixed one, all right? So we're taking the first one, which is fixed. And what do you know about a fixed? So take your ruler in your hand, right? Take your ruler or anything else that you've got that has reasonable, some flexibility, okay? So let's see if I can get my camera on here for a while. If I can show you what I'm talking about. Camera. Okay. I'll go back a little bit so you can pick up my hand and the ruler. Can you all see that? Hello?
Yes, we can see it.
Will you answer, please?
Yes, sir, we can see it.
Really like a pin, right? I'm holding it this way. It's firm. Guys, sorry about that. Okay, right. So that's fixed. What I'm saying about fixed is if I do something here, if I push it, can you see that the other hand do it with yours, right? With one hand you push, the other hand is resisting that movement. If it's not, it would just go with it, correct? So it's resisting that. If you push it vertically, you put force on it vertically, this hand can go down, but the purpose of the support is to make sure it doesn't. So you're resisting vertically with this force in the vertical direction. You push it horizontally, okay, you're pushing it that way. Your hand is reacting by pushing in the opposite direction. You put a moment on it, so you twist it, okay? Then your hand is resisting by opposing that direction. So that's what he's saying, right? Let's camera off there for a okay. The fixed one that all right. So when you look at the first, we can see straight away that there are no degrees of freedom. It cannot move vertically, it cannot move horizontally, and it cannot rotate. So no degrees of freedom. Look at the second one, it's a pin, okay? So we should keep the camera on for a while. Okay, the second one is a pin. So now what I've got is something like this. See the way it's free to rotate in one direction. In this direction, it can't rotate because of the way I'm holding it. So I got the pin here. Or vertically. Hello, can you hear me now? Please, I'd appreciate a response because otherwise it's going to stop this online class completely and we just wait till lectures are back to normal.
Yes.
Yeah,
Because
yeah,
we're
you're
having
back
issues
now.
with data, and the data at the moment is very poor. Okay. The Wi-Fi signal here, it is fluctuating, all right? So pen, I have, as I was saying, I have no resistance to rotation. Okay, I have no resistance to rotation, but I have resistance to vertical and horizontal movement. In other words, if I've got a pin support, it doesn't move horizontally, it doesn't move vertically, but it allows rotation. So it allows that column to rotate around that support. Then if I have a roller, the roller is rotation that is possible, but vertically I have one reaction. So in terms of vertical movement, so remember that's what we're looking at, is how many ways move, okay? So two ways, it can rotate, and what can rotate? The element that is connected to the support. In other words, that column can rotate, or it can move horizontally because the reaction is a roller. If I look at the intersection that we looked at earlier of two members in a frame, there's no support here. Okay, understand that there's no support at this point X. Are rigidly connected, and when you do steel design, you'll understand that what I'm saying is something like this is happening there. So I have
Boyo, may like a
Beep.
breakfast there.
right. Sorry, it's drawing is very crude.
Doing parking, walking around.
And then I put in bolts. Okay, and then I put in bolts there, and that is if I wanted a pin connection, then what I could have done is I could have had the same column, right? It's a steel column, so it looks like that in section. Are you with me? Okay, so it looks like that, and there's a beam. So looking at it from the top, that's what you're going to see. Okay, that's what you're going to see. And so, right, so that's what you're going to see there. And then your column in this case, you'll have a gap. You can have an end plate if you like, but you leave a gap. You'll put in a cleat here. Okay, and a bolt there and a bolt on that side. Are you with me? Okay, so you'll have a connection like that. All right, so that'll be a pin, but this one is rigid, so we can do this connection rigidly. Okay, so this is a rigid connection. There's no support there. So three things can happen, is that you can get, as I showed you, if it sways in one direction like that. Okay, it sways like that because you put in a force there perhaps. You can see that this thing has moved a certain amount horizontally. There may be a small degree of vertical movement, and of course this column has rotated, and so has that beam, because it won't be straight. It'll do something like that. Okay, it's going to do something like that. Right, so there's also rotation of the beam. So this is what we're saying, 3 degrees of freedom. Are there any questions? Are there any questions? Do you understand what we're talking about here? We're talking about degrees of freedom, not the reactions. Is everybody happy with that? Any questions for now?
Sorry, sir.
Yes, I'm
Yes,
listening.
I couldn't use screen for some time now, but now it's. But
Sorry,
I
I can't
don't
hear
know
you.
what you're presenting.
Sorry, can you speak a
Say
little bit
that I
louder?
could not see your screen for some time. Then I'm saying that I could not see your screen, but now I can see it. Can you just explain again or something?
What do you want me to explain again? This is a problem. That's why I want on-campus lectures and not online, because there's a data issue here. There's a problem with the internet. Okay, on your side or the device that you're using. On my side, I'm having a problem with the connection as well. But which part of it do you want me to explain again? Okay, so here's the sketches.
I think, yeah.
So let me ask you the question, right? So here we have a sketch here with different types of supports. So support number 1 is fixed, right? Support number 2, we have a pin. Support number 3, we have a roller. Support number 4, we don't have a support, we have a rigid connection, right? So which one? We're trying to see what each allows in terms of movement. Understand that, okay? And I've got a message here that says that I'm breaking up and you can't hear me. Unfortunately, that's the internet connection here at duty at the moment. Okay, there's nothing I can do about it. You don't want to be on campus. You want to be online, so there's nothing much that I can do about that right now. It's not in my control. Okay, so coming back to your question, fixed, there's no ways it can move in any direction, right? Pin, as I showed you, it can move rotation, it cannot move vertically, it cannot move horizontally. Roller, you have 2 degrees of freedom. One is rotational, okay, and it can move horizontally because the roller is placed, the wheels are placed on a horizontal surface. If you had a vertical roller, so if I had a beam, let's say, and I had a roller like this at the end, connected vertically to something, okay, then this will allow movement in that direction. Are you following what I'm saying? But this horizontally, it cannot move. It won't allow movement that way. Don't think of reactions, think of movement. Okay, all right, so roller will allow me, this thing can rotate. It'll be free to rotate. It's a pin, okay, and free to move vertically, but it cannot move horizontally. So I've got 2 degrees of freedom, right? A rigid connection, I've got 3 degrees of freedom. In other words, as I explained, this is part, for example, of a portal frame. It's a connection there between the beam and the column. So if I have sway, in other words, horizontal movement of the whole structure, then I end up with a horizontal displacement. I may get some vertical displacement, small though, and then I will get rotations in terms of angles. Okay, so that gives me 3 degrees of freedom. All right, does that help? Sorry, you asked me, those of you said it was not clear, and apparently from a message that I'm getting, it's not clear as well. Do you understand now? Does it help? Okay, does it help? Guy that asked the question.
Yeah, it's
Thank you
better
for
now.
it.
Thank you.
Did you? Better. Okay. All right. The connection seems to be, unfortunately, I can do nothing. The connection's going up and down here. All right, so let's try this then. Degrees of freedom. Let's go to the first one, which is a beam, which has got a pin at A. There's a pin at A. There's a pin at B, and C is fixed, right? So a pin doesn't allow you to move vertically. It doesn't allow you to move horizontally, but it allows a rotation. So that's 1. Okay. B, I have another pin, so it will allow rotation. It will not allow vertical and horizontal movement, so that's 2. Okay. C is a fixed end. It won't allow horizontal movement, won't allow it, won't allow vertical movement. These are not reactions. Remember, I'm drawing degrees of freedom, and it will not allow rotation. So nothing can happen at C. It is totally fixed, right? So therefore, my degrees of freedom are 2. Okay. Any questions on the first one? Is everybody happy with that? So you've got support A, which is a pin. We know it's got 3 reactions. If I ask you what's the total number of reactions in the structure, you will say 2 at A, R's. How many R's do I have? I have 2 at A, 2 at B, 3 at C. So I have 7, all right? I'm not asking you for that. I'm asking you what's the degree of freedom in the structure? How many ways can things move in the structure? So you will tell me, yes, at A, it can rotate. At B, it can rotate. At C, nothing can happen. It's fully fixed. Is that clear? All right, do you understand that? Good. Let's move on to the second sketch. I've got here, I've got A, B, C, D. So I'm just going to take this off so we don't confuse this anymore. That's gone. We dealt with that one. Let's look at this one. So A is fixed, B is a pin, C is a pin, D is fixed. So degrees of freedom at A, 0. Degrees of freedom at B, 1. Degrees of freedom at C, 1. Degrees of freedom at D is 0. total number of degrees of freedom is 2. So different structure. I've added an additional member. I've added an additional fixed reaction, but all I'm getting is 2 degrees of freedom. Okay. And I'll tell you why this is important just now. Right. So here I've got a portal frame in the third figure. So just for ease of reference, maybe we can just label them as figure 1, figure 2. Okay, so figure 3, we're done with figures 1 and 2. Let's look at figure 3. Support A, node B, node C, and support D. Okay, right? A is fixed. Degrees of freedom is 0. B is a rigid connection. It's not a support, it's a rigid connection. Okay, and we saw earlier in the explanation, it can move horizontally, it can move vertically, and it can rotate. And I will demonstrate this to you in the classroom in the physical lecture with a model, so you'll understand it better. Okay, so you can see I have rotation, I have vertical, I have horizontal, 3 degrees of freedom. Okay, then I have same thing happening at C. I have 3 degrees of freedom. And how many do I have at D? D is how many?
1.
1, correct.
1, sir.
So in total, how many do I have? 7.
7.
Right? Happy. Let's move on to figure 4. Okay, so here I'm going to have A. Let's call that A, B, C, D, and E. And then in this corner, we'll call that one F. A, how many degrees of freedom?
0.
0, correct. B, how many degrees of freedom? How many ways can it move? 3.
3.
Right. C, how many ways can it move?
0.
0. D, how many ways can it move?
3.
3.
And E, how many ways can I move?
1.
1. And of course at
1.
F, I've got a roller, so it's got 2 degrees of freedom, right?
2.
So I've got 2, 6, and 2 is 8, and 1 is 9. All right, so we've got 9. Okay, so when we do calculations, we assume that this thing is infinitely stiff. Right, so what we mean, it's not like our plastic ruler. We assume that it's a rigid. It's like something you can't bend, okay, in a hurry. So that's the assumption that we're making in terms of the what's connecting between the nodes. In regular computer analysis of structures, the identification of the degrees of freedom is one of the first steps. So when you put into a computer your structure model, when you model your structure into the computer, the first thing that the program wants to see or try and get out of what you put in is this: how many degrees of freedom does it have to deal with? Okay, and if I could just step out of this for a second and show you perhaps what a computer analysis looks like. Not a hand one. I can just let me see if I can find it quickly. I was going to pop into something that is called matrix methods. Okay. And just jump into this so you can see what is involved. Okay, so here's an analysis that we used to do for our BTEC students, with our BTEC students, a matrix analysis. So we're basically doing what happens inside the computer. When you're doing a computer analysis, this is what the computer is seeing. So we feed into the computer. You can see node 1, node 2, node 3, member 1, member 2. We feed properties of this thing. You're putting it into a program and it has certain inputs, certain outputs, certain calculations. So you have to look at member 1 has no degrees of freedom. Member 2 has 3, that's why it's identified as red. And node 3, sorry, has 3 reactions but no degrees of freedom. So I'm identifying the degrees of freedom in red. I'm identifying the reactions in black with hatches on them. So you can see that really all I have to first start off by getting is 3 unknowns. So then I set up stiffness matrices for each one. So one member is a 6x6 matrix, and then I extract what is common to both members, right? Because I'm looking at resolving that connection at 2, and I'm able to establish the stiffness matrix for the joint. Then I look at the loads and pull out the loads, and then the associated calculations, and it goes into solving for that. And at the end, I'm able to get, using matrices, of course, I'm able to get out the results. Okay, so I could get out here it is. So this is the displacements that I was looking for, right? So this is P1, the displacement 1, displacement number 2, and displacement number 3. It comes out in the results from the matrix using this P minus PF is equal to S over D. So I have to set up this whole matrix. So this is what the computer does in the background. So I'm just trying to show you. So the computer doesn't see your picture, it sees your input in terms of numbers and these kind of things. Okay, so where are we? Yeah, sorry. So what I'm saying to you is, if you could, in the computer, it can handle any number. Any number. I mean, the computers, you can put in 9 by 9 matrix, 50 by 50. It doesn't have a problem. When we do calculations by hand, the bigger the degree of freedom, the more the number of equations, and we have to solve the equations using matrices by hand. You can imagine it's going to be quite a mission. So what we do is we make some assumptions, reduce the number of degrees of freedom. Sorry, that shouldn't be dot. That should be DOF to the minimum possible. We assume that all of the members have infinite axial stiffness. So what we mean by that, for example, again, it's something I can show you in the classroom quite easily. And if I try to put on the camera, it's going to affect the data. That's what was happening earlier. So if you take you remember your ruler, your normal plastic ruler, and compare it to the one you used for drawing, the triangular one, the scale rule. And you can see that the scale rule is not flexible. You can't bend it, right? So it has a degree of stiffness, not 0. But if you take your normal plastic ruler that you use, it's fairly flexible, all right? So that AO is not very big, it's very small. Okay, so that's what we're talking about in terms of stiffness. So we assume that all of the members have infinite axial stiffness. That is, they do not extend or compress when subjected to tensile or compressive forces. They don't really become too big or too small. All right. It turns out that since flexure is the dominant type of action in this kind of structure studied here, the error induced is marginal and the assumption is found. So we're talking about the theory behind all of this. Referring to the third example above and applying this assumption, will be seen that since both columns are fixed at their bases, so let's go back to this one. So what we're saying here is, let me just get rid of all the garbage first, and then, sorry, not the garbage, all the stuff we scribbled on. Okay, so what I'm saying to you is we're going to this third sketch, and on the third sketch, can we make something simpler by assumption? In other words, if I have an infinitely stiff member between A and B, so that's A and that's B, so that's C and that's D, right? So I have an infinitely stiff member from A to B and an infinitely stiff member from C to D. Is this going to happen?
No, sir.
No. Okay, but do you understand what we're talking about, right? We're saying, see that in isolation. Sorry. So I have a column. So I want you to imagine a column now, right? And it is supported there, and it's nice and big. Okay, so there's my support here at the bottom. It's a nice, big, heavy column. All right, and I put a load on it. Okay, so it's nice, it's fat, it's a big concrete column. All right, and I put a small load on it. Is stiff? That means it's very, very rigid. It's very, very strong. Unlikely, right? So that assumption is saying that if this is going to be the response, then I'm not going to get any movement vertically. Okay, then I can say, okay, simplifying assumption that it's almost negligible. It's almost zero. Then in that case, I can take that one out. I can take this one out. Let me use another color to. Okay, so that one can come out, and so can this one. Both of these can come out, right? So those 2 degrees of freedom I can ignore. They are there. I don't say they don't exist, but they're very, very, very small. It will make no significant effect on my calculation. So this 7 can be reduced to 5. Now I still look at something else. The displacement A and B. So if I have a deflected shape which goes like this and like this deflected shape is slightly different, and this one is pinned, and then I have that happening at the top. So this line that I've drawn now is the way the structure deflects, how it looks when it's deflected. What can we say about the deflection at B and D horizontally? What do you think? Are they different? Remembering that BD is something very, very stiff. Okay, it's got infinite stiffness. Stiffness is measured with inertia divided by length, right? So it's infinitely stiff. Okay, so I've got a big fat section, and it doesn't really get flexible, or it doesn't shorten or elongate in a hurry, right? So when I move these two, so what you can do is take your ruler, put it between your hands, right and left hands. You'll see, right? You will notice that the deflection is identical at both ends, right? So I can take those two deflections and say that they are equal. Are you with me? So delta HB, delta HD. So using that, I can say, now hang on, that means rotation at B. I've got rotation at D, and then I've got rotation at C. Okay, so I've got 3 rotations, but instead of 2 displacements, I can call them 1 because they are equal. Are you with me? So now I can reduce it to 4. Okay, so I can simplify that one to 4. There we have it there. So I can reduce it to 4, 5 or 4. Okay, are you with me? And then when I come to this one, what do I notice? I can take that out. It's infinitely stiff. I can take that out. It's infinitely stiff because the support here and here are going to hold it in position. And then I can horizontals, obviously, depending on the kind of load. This could move horizontally, but because this is very, very stiff, it's not really going to go anywhere. So even the 3 horizontal reactions will be negligible, and you'll be left with the 2 rotations. Okay, so that you could reduce to 4. Those rotations, sorry, not 2 rotations, 4 rotations. But I could remove the horizontals and verticals. So what I would like you to do is just attempt this, and then I will discuss it with you the next time we meet. It's not the end of the lecture, but I want you to do this. You just have to make an assumption, all right? Just see what you think, how many ways it could move, where it could move, all right? And remember, we're talking about the movement of the member about the connection. All right, so attempt this one, and then the next time we meet, we will go through it together. All right, I think I will leave the tutorials for when we get back to campus. I will do it with you then. Okay, so but please attempt this. So what I want, this is what I was saying to the students that came yesterday to collect the notes. I don't have a tutorial session, although the timetable it shows tutorial. I use it for both lectures and TUTS. So what I do is I have a lecture, and when I finish the lecture, I give you the tutorial, and at the next lecture, right, or tutorial session or whatever it is called, I go through the tutorials of what you have to do. So one section builds on the other. All right, you remember Stroud, the textbook that you use for maths? You got to go through frame 1, answer the questions. When you've answered that, then you can move on to frame 20. If you haven't done frame 1 to 19 first, you won't know what's happening in frame 20. Okay, so you got to keep going from the beginning, right? Any questions? Degrees of freedom. So this is just to help us understand the structure. Okay. Is everybody happy with
So
degrees of
I have a
freedom?
question. Yeah.
Sure, please shoot.
Yeah, when you introduced the infinite stiffness and then you started removing some degree of freedom,
Correct. Yes.
like how do you know which ones you meant to remove and which ones you're
Because
not meant
what
to
you're
remove?
looking at, okay, let me explain that part again. Okay, what I'm saying to you is what you need to see is, can that structure really, can that element really is there really any movement at the connection if it becomes infinitely stiff? Okay, so let's take one part of this only so we can talk about it. Sorry, trying to get rid of some of this. A second. Right, so looking at this column again. So if you've got your scale rule with you, you know the scale rule, the triangular one, have you got it with you? Please, I need you to put that in your hand. Okay, and then I want you to put a load on the top of it. So put it down on something, or you can hold it at the bottom with your hand, fix it. Right hand, put a point load on that thing at the top. Okay. Do you notice any change in the length of the ruler?
No, sir.
Vertical, no. Reason is that in relation to the load, the size of this member, right? It's the way it's made up. It's infinitely stiff in relation to its length. Okay. If you had made it taller, if you took the same ruler and you made it 10 meters long, with me, and then you put that point load, like possibly what could happen? 300 mils, or what is it? Yeah, 30 centimeters or 300 millimeters long in the physical one, that model that you got in front of you, right? You put a load on it, a point load on it. Okay, sorry, I wish I could turn the camera on, but I risk losing you again, so I'm scared to do it. because that's what's happened previously. So your triangular shaped ruler, I put a point load on it. I'm holding it at the bottom, or I can leave it on the desk if you like, and then put a point load on it, and you can see nothing significant is happening. It's not getting any shorter. It's not moving out sideways, nothing, right? That's infinitely stiff. So vertically, there is no shortening. Sorry, so to put it on the diagram here, what I'm saying to you is I don't get delta V. Okay, so this thing doesn't happen. It's negligible, or it's 0.0000 something. Are you with me? It's so small we choose to ignore it. Does that make sense to you?
Yes, sir.
Okay. Now I want you to take your normal ruler. You know, the plastic one we use, right? Not the scale ruler, just the plastic simple one, and put that on the table or on a top and put a load on it. And what happens as you start increasing the load? What's going to happen? The ruler starts to bend, correct? Are you with me? Okay.
So
It starts to look like this. So you have it, you held it down here somewhere, and you put a load on it and you kept it in position. What will happen is this thing will start to go like that, correct? But now, as it's doing that, you notice that it's shortening. Do you agree? And now I can see the delta V, and as I increase the load, that delta V becomes bigger. Do you follow what I'm saying to you? Okay, so this one, the stiffness AE is equal to infinity. Do you follow? And this has a stiffness that is very, very small. So this is very large. Do you understand? Does that help you?
yes, sir.
If you're still stuck with it, just bear with me and remind me, please, to show you the model in the classroom next week.
So,
Okay.
sir, does the same principle apply in the horizontal direction?
Right, is that okay? Any other questions there?
So does the same principle apply in the horizontal direction?
Yes, if you for the horizontal, of course. Now, don't forget. But like here, remember here, I could take the horizontals off. Good question. Here I could take it out. Why can't I take it out? I can take it out in 4. Why can't I take it out in figure 3? Sorry, that's figure 3 and this is figure 4, right? Figure 3, but not take it out in figure 4. Sorry, other way around. Why could I not take it out in figure 3 and take it out in figure 4?
Because figure 3, it lacks supports.
Correct, 100%.
Yeah.
Exactly.
Okay.
So if anybody still hasn't understood it, guys, I've showed you my timetable, right? Okay, I need to create some consultation times as well. But outside of that, please try and feel free to contact me. You can try it on Teams as a live call for now. But as I said, come to campus. Just come to the office. Just can help you. And we'll be 2 minutes. Okay. Any other questions on this?
Yes, sir.
Yes.
Do we always have to treat it as if there's an infinite amount of stiffness, or is it just in certain cases?
When we're doing this analysis, yeah. When we're doing our analysis, this is one of our assumptions. Because the minute we move away from that, we introduce other unknowns into our problem.
Okay, so we always treat it in that way.
Okay, let me give an example. Yeah, because in reality, our structures, our beams and columns are stiff members. Now imagine if you made a structure with drinking straws, right? We've all done that at some stage, playing around in school or wherever. We use drinking straws, just a normal round drinking plastic straw, paper straw. Now imagine you've created a structure with that, and you know it. What's going to happen? Okay, or try another one. Take the drinking straw between the fingers of both your hands, right? And just pull it apart. What do we notice? Lots of times we do that when we drink our can of Coke or whatever, and we just take the straw and we play with it sort of unconsciously while we're doing something or talking or whatever, and we stretch it, we pull it, and as we pull it, what do we notice? It tends to become thinner, right? Now that wasn't infinitely, I mean, it's not very stiff, that's right. And if you bend it, you can just bend it over in two, correct? And you'll get a line in the sort of middle where you've bent it over. So you follow what I'm saying? Whereas a concrete column or a concrete beam or a steel beam or a steel column is a lot different to that straw. Do you follow what I'm saying?
Yes, no, I
Does
understand.
it make sense to you?
Yes.
Okay. Good.
Thank you.
Right. So just give this one a shot. Just have a look at it. This is very, very basic introductory stuff, right? So have a look at it, just try it out. It's just to get your understanding about degrees of freedom, okay? And we will use it when we come to slope deflection and virtual work. And the first method, we don't really concern ourselves with is moment distribution. We don't concern ourselves too much with degrees of freedom. We just look at how many unknowns we have to solve for in terms of reaction. So there's different methods have different things that we concern ourselves with. All right. Okay, so that's degrees of freedom. I'll stop with that for now. So that's the first part of our lecture. Let's stop this recording. So we put it into 2 parts, and then I want to. So let me stop this recording.